Alright, in this video we're going to look at multiplying radicals and radical expressions. Directions here say multiply as indicated and then simplify. So here we have the square root of 2 times the square root of 3. So if you're multiplying radicals, now first thing we need the index of the radicals to be the same. So here we're multiplying square roots, so their indexes are the same, both 2. Now, unlike with adding or subtracting with radicals, the radicands don't have to be the same in order to multiply. All right, and the way that we multiply radicals with the same index is we're going to keep the radical same index, and we're going to multiply the radicands. So here we've got the square root of 2 times the square root of 3. So what we'll do is when we multiply, we'll have the square root, and then we're going to multiply 2 times 3. Now, what I typically do when I multiply is underneath the radical, I just write down the multiplication, but I'm not going to perform it right up front. And the reason is because once we multiply, we then need to simplify the radical. And to simplify the radical, we start to factor the number that's the radicand, and then in order to simplify. And so if I multiply and then try to factor, that's kind of counterproductive. And so I'm going to write down the multiplication and then see can I factor it any further or simplify what we have. So since we're dealing with the square root here, we either want a factor we know the square root of, or 2 of the same factor. Well, 2 is prime, 3 is prime. They're not the same. We can't factor them any farther, so this will not, the square root won't be able to simplify from here. So I'm going to go ahead now and multiply 2 times 3 to get 6. So we're going to have the square root of 6. And again, that will not be able to simplify any farther than that, and so that's how we will write our answer. Alright, so let's look at this next problem. So let's say we have the square root of 6 times the square root of 15. So we're going to go through this similar to the first one. So I'm going to say the square root of 6 times 15. Alright, I'm not going to multiply them just yet. I'm going to try to see if I can factor this and see if we'll be able to simplify the radical. And so 6 we can write as 2 times 3, and 15 we can write as 3 times 5. Right? So I wrote the 6 as 2 times 3, and then I wrote 15 as 3 times 5. Right? 2, and so now each one of these factors, 2, 3, 3, and 5, they're all prime, so we can't factor any farther. And with the square root, index is understood to be at 2, and so we're looking for 2 of the same factor, and we've got 2 factors of 3, so we're going to be able to simplify that. All right, so square root of 3 times 3 is 3, so we'll put 3 in front of the radical, and underneath the radical, we're still going to have 2 times 5. And so we can go ahead and multiply 2 and 5 back to get 10. And so that simplifies down to 3 square root of 10. All right, so now let's look at this. So here we're multiplying not just radicals, but radical expression, or expression that has a radical in it. And these two expressions have 2 terms, right? We got 5 minus the square root of 7 times 2 plus the square root of 10. And so we're going to use the FOIL method, right? So we're going to go through and FOIL. So FOIL will do first term, so 5 times 2, right, which will give us 10. And then outside, 5 times the square root of 10. Now, when we multiply 5 times the square root of 10, 5 is not in a radical, and then here we do have a radical, so don't multiply 5 times 10 and get 50, right? We just have to write it down, 5, and then times the square root of 10, right? We really can't do anything as far as multiplying 5 and 10. And then we do inside, negative square root of 7 times positive 2. Again, one's in a square root, one's not, so we just have to write it -2 times the square root of 7. And then last, negative square root of 7 times positive square root of 10, so it's going to be negative, and both of these are square roots, and so we keep the square root and we multiply the radicand. 7 times 10, which will give us 70 underneath the radical. Now, we need to go through and see, can we simplify any of these radicals? Square root of 10 will not simplify. We can break 10 as 2 times 5, but that doesn't lead to us being able to simplify the square root. Square root of 7, 7's prime, can't simplify that. Now 70, we could factor 7 times 10, and then factor 10 is 2 times 5. So the prime factorization of 70, 2 times 5 times 7, but that again will not lead to us being able to simplify the square root of 70. Now the only terms that we can combine as far as when we're adding and subtracting that involve radicals, they all have to have the same radical with same index and same radicand. Well, none of these have the same exact radical, right? This first term is just 10. There's no square root. Here this is square root of 10. Here this is square root of 7, and then square root of 70. All their radicands are different, so we can't combine any of these terms. So this is as simplified as we can write it. All right, we don't want to type in our calculator because we would then have to round, and we want exact answers here. All right, now before we look at this next problem, I just want to make just go over this. If you multiply square root to itself, right, square root of a times square root of a, well, that's going to be the square root of a times a, which is just going to be a, right? So a square root times itself is just like taking a square root and then squaring it. Is just going to be the radicand a. All right, and that's going to be something we'll see in use in this problem. So let's look at 10 minus the square root of 11, that quantity, times 10 plus the square root of 11. All right, so you may notice here something that's kind of unique is the terms in each of these parentheses are the same, except one's a difference and the other is a sum. Right? When that happens, we call these two conjugates. 10 minus the square root of 11 and 10 plus the square root of 11 are what we can call conjugates. And when you're multiplying conjugates, you really don't have to use the entire FOIL method. You can just do the F and the L, the first and last, right? Because when you multiply the outside terms and then multiply the inside terms, those terms, when we go to simplify, are going to add to 0, right? But I'm going to go ahead and go through the entire FOIL process here. So multiply first. So 10 times 10 will give us 100. Then we're going to do outside. 10 times the square root of 11. Then inside, negative square root of 11 times 10. So that'll be negative 10 square root of 11. And then last, negative square root of 11 times positive square root of 11. So it's going to be negative, and the square root of 11 times itself is 11. Now if you notice, the terms in the middle, positive 10 square root of 11 minus 10 square root of 11, have the same exact radical, square root of 11, so we can combine them. And so you would keep the square root of 11 and perform the operation between their coefficients, and 10 minus 10 is 0. 0 square root of 11 is 0. Right? So the terms in the middle are going to add to 0. Now, we also have these integers, 100 minus 11. We can combine that, that'll give us 89. And again, as I said, 10 square root of 11 minus 10 square root of 11 is 0. And so we're just left with 89. All right, and again, you can see we could have gotten away with just doing first 10 times 10 is 100, and then last, negative square root of 11 times positive square root of 11 is negative 11. 100 minus 11 is 89. And so we get this note here that if we're multiplying conjugates, and I wrote down the specific case where you basically got an integer plus a square root and then an integer minus a square root. When we go to do this, we can just do first terms, a times a is a squared, and then last, positive square root of b times negative square root of b is negative b, right? And so that is what happens when you multiply conjugates that involve a square root, right? And that's something that we're going to use when we go to rationalize denominators.